You know, if you really stop to think about it, the electricity coming out of your wall is kind of violent. Depending on where you live, you've got hundreds of volts of alternating current just aggressively reversing direction 50 or 60 times every single second. Yet somehow, when you plug in your incredibly delicate smartphone, it receives this perfectly calm, steady trickle of 5-volt direct current. So, how exactly do we tame that wild, aggressive wall power into the steady energy our sensitive electronics need to survive without, instantly frying? Welcome to This Explainer. Today, we're going on a pretty fascinating engineering journey. We're going to dive into the exact physical path electricity takes to become safe and usable for our devices. It is an incredible story of transformation, filtering, and extreme precision that literally keeps the modern world running. Here's our roadmap for today. We'll start with the AC problem, move on to rectification, smooth things out with filtering, and finish up with regulation. All right, looking at the big picture here, our wild AC supply immediately hits a step-down transformer to lower that dangerous voltage. From there, the signal travels through a diode rectifier, passes through a filter, and finally enters a voltage regulator to become a perfectly steady DC output for our load. Notice those wave graphs at the bottom? They perfectly illustrate how the power physically changes shape at every single stage. Let's actually look a bit closer at that second block. Section 1. Rectification. Directing the flow. So our first major challenge after stepping down the voltage is stopping that back and forth flow of AC. Because our devices don't want alternating current, they absolutely need direct current. We have to force the electricity to move in only one direction. In engineering terms, this is called rectification. It's the process of converting that smooth, reversing AC waveform into unidirectional, single polarity half cycles. Think of it kind of like taking a chaotic two-way street and turning it into a one-way highway. Rectifiers act essentially as one-way valves for electricity, and while they completely solve our direction problem, as we'll see, they create a brand new problem along the way. To actually achieve this one-way flow, we use what's called a bridge rectifier circuit. Now, instead of just using one diode, which would block half our power and waste it, this bridge uses 4 diodes working together in a really clever diagonal partnership. When the AC wave swings positive, 2 diodes open up and let power through to the load. Then, when the wave swings negative, the other 2 diodes instantly take over, essentially flipping that negative wave upwards. The result? Both halves of the AC cycle are perfectly converted into a pulsating, forward-moving DC signal. We aren't wasting any power at all. But okay, this one-way street isn't exactly smooth yet. The electricity is pulsing, dropping all the way to 0 between every single wave. This undesirable fluctuating leftover AC component is called the ripple. The ripple factor is just a mathematical measurement of this leftover mess. And let me tell you, it is the absolute enemy of stable electronics. If you fed this pulsing power directly into an audio amplifier, for example, you would just hear a massive, awful humming sound. When you compare the different designs, the bridge rectifier emerges as the clear winner for modern equipment. It boasts a maximum efficiency of 81.2% and a relatively lower ripple factor of 0.48. Plus, it pulls this off without needing a bulky, heavy, and expensive center tap transformer like the older full-wave designs did. But wait a second, a ripple factor of 0.48? That is still a massive fluctuation. Section 2. Filters. Smoothing the bumps. Yeah, even a ripple factor of 0.48 is way too high. Delicate equipment usually needs a ripple factor below 0.001. So to get there, we can't just change the diodes. We need to fundamentally change the shape of the wave itself. We need an electrical shock absorber. Enter the RC, or capacitor filter. By just adding a capacitor in parallel with our load, we create a tiny temporary energy storage tank. As the rectified wave peaks, the capacitor charges up. Then, when the input voltage inevitably starts dropping back down towards 0, the capacitor steps in and slowly discharges its stored energy right into the circuit. It literally fills in the valleys. By doing this, we've successfully transformed those deep, aggressive pulses into much shallower, gentle ripples. But for truly superior smoothing, engineers step it up to something called a pi filter, named because the circuit diagram actually looks like the Greek letter pi. This beautifully combines 3 components. It uses a first capacitor to bypass high-frequency AC ripple to ground, an inductor right in the middle which physically resists any changing AC currents while letting steady DC pass, and then a second capacitor to mop up whatever tiny bit of ripple managed to sneak through. It is an incredible multi-stage defense against unstable voltage.
Section 3. Voltage Regulation, the final polish.
So our power is finally smooth. But we aren't quite done. Because even with smooth power, surges from your power company can still cause your voltage to drift dangerously up or down. We need a hard lock on that voltage. Enter the Zener diode. Now, standard diodes are destroyed if you push current through them backwards. But a Zener diode is a very special silicon device designed specifically to operate in what's called the reverse breakdown region. Once the voltage hits a specific threshold on the curve, let's say exactly 5 volts, the Zener diode suddenly opens up and lets current flow backwards. It acts exactly like a nightclub bouncer, bleeding off any excess pressure to maintain a perfectly constant output voltage, completely regardless of incoming surges.
While Zener diodes are definitely brilliant, technology marches on. Today, rather than building these complex circuits with individual diodes and resistors, engineers rely heavily on modern integrated circuit, or IC regulators. These modern microchips are incredibly cheap, they're super simple to wire, and they feature built-in superpowers like thermal shutdown, meaning they'll automatically turn themselves off if they get too hot, and short circuit protection. That makes them virtually indestructible. The wildly popular fixed voltage regulators basically hand you the resume right in their name. Take the legendary 78XX series, for example. The 78 guarantees a positive voltage output, and the XX at the very end tells you exactly what that voltage will be. So a 7805 gives you a rock-solid 5 volts. A 7812 gives you exactly 12 volts every single time. It completely takes all the guesswork out of circuit design. When you build it into a finished circuit, just look how beautifully simple this is compared to the massive bridges and filters we started with. This little 3-terminal chip takes our filtered, still slightly bumpy input on pin 1, dumps any excess noise directly to ground on pin 2, and uses its internal microscopic transistors to deliver a perfectly safe, perfectly stable, and completely flat voltage right out of pin 3. Add 2 tiny capacitors to prevent oscillation, and boom, you have a flawless power supply. But what if you're designing a custom device and you don't want exactly 5 or 12 volts? What if you need exactly 3.3 volts, or maybe 9 volts? Well, engineers use adjustable chips like the incredibly versatile LM317. By just twisting a tiny external variable resistor, you can literally dial in the exact output voltage you need anywhere from 1.25 all the way up to 37 volts. It offers total programmable control while still maintaining all that awesome thermal and overload protection. Ultimately, this entire journey dictates the lifespan of your devices. An unregulated power supply essentially leaves your electronics at the absolute mercy of a chaotic world, surges, dips, and changing demands. But a regulated power supply, its output remains perfectly constant. We've successfully taken a wild, dangerous, alternating wave and engineered it, through rectification, filtering, and regulation, into dependable, life-giving energy for our technology. We've absolutely mastered the art of taming wild AC into safe DC using transformers, diodes, capacitors, and silicon ICs. But as our microelectronics become unimaginably smaller, operating on mere fractions of a single volt, and our power grid faces new unprecedented demands, it definitely leaves us wondering, how will these fundamental building blocks evolve next? What will the power supplies of tomorrow look like to protect the hypersensitive technology of the future? Thanks for joining me on this explainer. I hope you never look at a standard wall charger the exact same way again.